Hello students, welcome to today's session of chemistry. As you all know, we have started studying fifth lesson of your syllabus, that is electrochemistry. Before starting today's session, we will just revise what we learned in the previous session. In the previous session, we learned about the concept of molar conductivity. It is the electrical conductance of 1 mole of an electrolyte, in short we can say. We also learned relation between K and lambda. What is K? It is electrical conductance of 1 cubic centimeter of solution. And what is lambda? Just I told you, it is conductivity of 1 mole of an electrolyte. And the relation between these two is given by Kohlrausch, and it is lambda equal to K upon C. As concentration is exactly opposite to that of dilution or volume, so the same formula can be written as lambda equal to K into V or K upon C. And in common units, we got the relation as lambda equal to 1000 K upon C, and the unit will be per omega square centimeter into per mole. And then we learn about the variation of conductivity and molar conductivity with concentration. Now, in case of electrolytic conductivity, on dilution, electrolytic conductivity decreases. On dilution, actually, the number of ions increases. Why? Because of the increase in degree of dissociation. What is degree of dissociation? You learn in ionic equilibrium. The lesson ionic equilibrium. So, number of ions increases, but that increase is not in proportion of the volume or dilution. Hence, number of ions per cubic centimeter actually decreases, and hence electrolytic conductivity decreases on dilution. Exactly reverse is the case with molar conductivity. As on dilution number of ions increases, molar conductivity increases on dilution. Straightforward. Because number of ions increase on dilution, and hence molar conductivity increases on dilution. Now, in continuation with that, we are going to learn about the variation of molar conductivity with concentration in case of two different types of electrolytes, that is strong electrolytes as well as weak electrolytes. So let us start with the session. So variation of molar conductivity with concentration in case of strong and weak electrolytes is qualitatively different. That means for strong electrolytes, it behaves differently, and in weak electrolytes, it is different. So let us start with strong electrolytes. Suppose we have prepared a solution of strong electrolytes and we diluted it. Then the molar conductivity of solution of strong electrolyte increases rapidly on dilution. So on dilution, it goes on increasing. It approaches the limiting value for 0.001 molar or for 0.001 molar solution. Limiting value, that means on further dilution, it has no effect on molar conductivity thereafter. So, we are diluting the strong electrolyte solution. The number of ion goes on increasing, hence molar conductivity goes on increasing. But after a certain period, it stops, or there is no increase in the molar conductivity. Why? Because it has reached limiting value. And what is that limiting value? That is, there is no increase or decrease in the molar conductivity after further dilution. The maximum limiting value of molar conductivity is the molar conductivity at zero concentration, it is said, or at infinite dilution. It is denoted by lambda 0. Infinite dilution or zero concentration means there will be no further increase in the molar conductivity after this dilution. Hence, it is zero concentration. Understood? It happens for strong electrolytes. Now, the zero concentration or infinite dilution means the solution is so dilute that further dilution does not increase the molar conductivity. Understood? Hence, it is zero concentration. During 19th century, F. Kohlrausch, with repeated experiments, showed that the molar conductivity of strong electrolytes varies linearly with square root of concentration. That means for all these dilution or relation between molar conductivity of strong electrolytes has been given by one equation by Kohlrausch. And the equation is lambda equal to lambda 0 minus a root c. Do you know all the factors here? What is lambda here? It is the molar conductivity. What is lambda 0? Molar conductivity at 0 concentration or at infinite dilution. A is a constant and C is concentration. This is the equation given for strong electrolytes. Lambda equal to lambda 0 minus A root C. Now, to find out the lambda 0 values in case of strong electrolytes, we have to plot a graph of lambda versus root C. Why? Because the for strong electrolytes, this graph is linear. How? It is like this. So this is the graph. It has two lines you see, but this curved line belongs to weak electrolyte and this linear or straight line belongs to strong electrolyte. So if we plot a graph of lambda versus root C, what we see? Strong electrolytes, there is a linear graph or that equation lambda equal to lambda 0 minus a root c, and we get a linear line or straight line. Now, what happens for weak electrolytes? The molar conductivity of weak electrolytes that also increases rapidly on dilution. And again for concentrations of 0.001 molar or for 0.001 molar, the lambda value is lower than lambda 0. Lambda is molar conductivity. Lambda 0 is the molar conductivity at 0 concentration. But for 0.001 molar or 0.001 molar, the lambda value is lower than lambda 0, which is the molar concentration at 0 concentration. What does that mean? Again, if we plot the graph, then we see that lambda or this curved line we get for weak electrolyte. So, the graph of lambda versus root C, for strong electrolyte it is a straight line, and for weak electrolyte the variation is like this. It is not linear. Hence, if we want to find out the lambda 0 value for strong electrolyte, any strong electrolyte, then just by plotting this graph and by extrapolating this, we will get this lambda 0 value here. Just by extrapolating, just by increase this line and touch it to y-axis where there is lambda, and where it touches that value will be lambda 0. So for any strong electrolyte we can find out the value lambda 0, and which is not possible for weak electrolyte because it is not touching that y-axis here which is for lambda, and hence for weak electrolytes we have to use different equation, and it is same is been told here. Molar conductivity of strong electrolyte at 0 concentration can be determined by extrapolation of linear part of lambda versus C curve. This method cannot be used for weak electrolytes since lambda versus C curve does not approach linearity. So we can't say that it will go in the same way, but it is a curved line. Hence, Kohlrausch law is useful for calculating lambda 0 for weak electrolytes. So he has given one law for calculating lambda 0 of weak electrolytes. And from that law and that equation dependent upon that law, we can find out the lambda 0 value for weak electrolytes. Understood? For strong electrolytes, we can directly plot a graph, and by extrapolation method, we can find out the lambda 0 value. Now, what is the Kohlrausch law for weak electrolytes? Now, and this law is very important. Now, just see the statement of the law. The law states that at infinite dilution, each ion migrates independent of coion and contributes to total molar conductivity of an electrolyte irrespective of the nature of other ion to which it is associated. Now we will see partly by partly this law to understand it in a better way. Now what is the law? Law is for the electrolytes at infinite dilution. Suppose we have prepared a solution of any electrolyte and we dilute it to its up to its infinite dilution. Now, at this dilution, each electrolyte, when dissolved in water, it will produce one cation and one anion. There is one positively charged ion and one negatively charged ion. You have seen dissociation in ionic equilibrium also. Suppose we have prepared a solution of KCl salt, then it will produce K plus and Cl minus ions. We have prepared a weak electrolyte like CH3COH, and if we dissolve it in water, it will produce CH3CO minus as anion and H plus as cation. So every electrolyte will produce one cation and one anion. But what happens at infinite dilution according to this law? At infinite dilution, these two ions have no relation with each other. They migrate independently, they move independently. Actually, because of their charges, they have relation with each other. There is force of attraction between cation and anion. But at infinite dilution, what happens? These ions, each ion migrates independent of coion, and thus that contributes to total molar conductivity of an electrolyte irrespective of the nature of other ion to which it is associated. That means each ion contributes its own molar conductivity, and hence if we want to calculate total conductivity of an electrolyte, then we have to add the molar conductivities of cation and anion. So this is the law. What it does, it tells at infinite dilution, each ion migrates independent of coion and hence contributes to total molar conductivity. Now, we will just take an example. Both cation and anion contribute to molar conductivity of the electrolyte at zero concentration, and thus lambda 0 will be the sum of molar conductivity of cation and that of the anion at zero concentration. Thus, this will be the formula then. Total conductivity lambda 0 at infinite dilution will be equal to n plus into lambda 0 plus n0 minus lambda 0 minus. Now let us understood what does it exactly means. Here n plus, that is number of cations in the formula itself. What is lambda 0 plus? Small lambda 0 plus? It is the conductivity of cations of n number of ions, n number of cations. N minus, that is number of anions in the formula, and lambda 0 minus will be the conductivity of those anions. That means total molar conductivity will be sum of the molar conductivities of cation as well as anion. As in case of some electrolytes, when we dissolve one molecule, it gives two cations or sometimes two anions or more than that also. For example, suppose we have taken AlOH thrice as electrolyte, then in water, how many cations and anions it will produce? Al plus 3, only 1. But OH3, that means 3 OH minus ions. So N plus and N minus will count the number of ions produced every time. And total number If we add the molar conductivity of total number of anions and cations, then we will get lambda 0, that is molar conductivity. This is all for weak electrolytes. For strong electrolytes, the method is simple. Just draw the graph and just by extrapolation method, we get lambda 0 value. Now, how this equation can be applied? Now, this same is told here. Lambda 0, lambda plus and lambda minus are the molar conductivities of cation and anion respectively, and n plus and n minus are the number of moles of cation and anion specified in the chemical formula of the electrolyte. Now, let us take the applications in which we will study, actually will apply this law. So, applications are equally important. First application. The theory can be used to calculate the molar conductivity of an electrolyte at the zero concentration. How? For example, suppose we have to calculate the molar conductivity of KCl. What will be the formula then? Lambda 0 of K plus and lambda 0 of Cl minus. That is the formula of Kohlrausch law. But suppose we have taken the example of BaOH twice. Now the factor n plus and n minus come here. Lambda 0 of Ba plus 2 ions and lambda 0 of OH minus ions, but 2 OH are there, hence 2 we have to multiply it by 2. So lambda 0 of Ba plus 2 and lambda 0 of OH minus of 2 ions. So first and most important thing, write down the dissociation equation as we learned in the ionic equilibrium. So BaOH twice will dissociate as Ba plus 2 plus twice OH minus, and then we can write this equation. Understood? So this is the first application of here. By knowing the molar conductivities of ions at infinite dilution, lambda 0 values of electrolyte can be easily obtained. Now, second application. This theory is particularly useful in calculating lambda 0 values of weak electrolytes from those of strong electrolytes. To understand this, let us take an example. For example, suppose we want to calculate lambda 0 of acetic acid. Acetic acid, CH3COOH, it is weak electrolyte. Then, lambda 0 of acetic acid can be calculated by knowing those of lambda 0 values of HCl, NaCl and CH3CONa, that is sodium acid. All three are strong electrolytes. Which are strong electrolytes? I told in the previous session. Strong acids, strong bases and salts are strong electrolytes, and weak acids and weak bases are weak electrolytes. As acetic acid is a weak acid, hence it is a weak electrolyte. But all these are strong electrolytes. If we know the lambda 0 values of all these three, then we can find out the lambda 0 value of acetic acid. As these three are strong electrolytes, just by plotting the graph and extrapolation method, we can get the values of all these three strong electrolytes. Now, for that, we have to use one formula. Now, lambda 0 of HCl if we calculate it, then lambda 0 of sodium acetate, and if we subtracted lambda 0 of NaCl, then we will get lambda 0 of acetic acid. So, formula is like this. To get lambda 0 of CH3COH, what we have to do? We have to take the molar conductivity at zero concentration of HCl, that of sodium acetate, and from that we have to subtract value of lambda 0 value of NaCl. Now, how? Let us see. Lambda 0 of HCl, according to formula, what will be the distribution or separation? Lambda 0 of H plus plus lambda 0 of Cl minus. For sodium acetate, the value will be lambda 0 of CH3CO minus and lambda 0 of Na plus. And the same way for NaCl, minus lambda 0 of Na plus minus lambda 0 of Cl minus. Now cancelling common ions, lambda 0 of Cl minus plus and plus minus lambda 0 Cl minus. As this is plus and this is minus, same ion, so it will be cancelled. The same way Na plus and lambda 0 Na plus and minus lambda 0 Na plus, those will be cancelled. What will remain? Lambda 0 of H plus and lambda 0 of CH3CO minus. That means, according to Kohlrausch law, it will be lambda 0, capital lambda 0 of CH3COH. Actually, we can't find out the value of this. But as we know all the values of these three, we can calculate it by using this method. And we will get, by using this formula, value of lambda 0, or lambda 0, that is conductivity at infinite dilution of weak electrolyte, can be calculated. For that, so lambda values of strong electrolytes HCl, CaCO, and NaCl, as we know, those can be determined by extrapolation method, and the lambda 0 value of acetic acid by using this formula can be calculated. So this is the application of Kohlrausch law. Now, time for assignment. This is assignment number 4. First is state and explain Kohlrausch law. Very important law. Very, very, very important law, you can say. Because many times it is asked in board exam for 2 marks. So, state and explain. That means you have to take one example and explain it. Again, second is explain applications of Kohlrausch theory. It's a table example. Just now I told you. In explanation of Kohlrausch law, here you can give that formula. Lambda 0 equal to n plus into small lambda 0 plus n minus into small lambda 0 minus. That is explanation. Understood? So, thank you.